So here we are in chapter 4. We're right about this area right now. So far we've learned some general properties of aqueous solutions, 3 different types of reactions, and now we go into the mathematical area by putting some math to some of these concepts we've already learned. Since solutions are a solute dissolved in a solvent, this allows us to calculate what's called a concentration for each one of these solutions. And that's what we're going to focus on today. And this is the section in the 13th edition of Brownlee if you're using that textbook. If not, it's the same concepts. So the unit that we use to calculate concentration most prevalently in chemistry is called molarity. Molarity is symbolized by a capital M, and molarity is equal to the moles of solute, that's the substance that is in the least amount in the solution, divided by the liters of the entire solution. So it's moles divided by liters. This can be illustrated in a triangle. And then the triangle is really easy to calculate, either moles by covering up moles, it's molarity times liters, volume by covering up liters, and it's moles divided by molarity, or molarity, which is moles divided by liters. So molarity is equal to moles divided by liters. And the units on molarity are moles per liter, or moles times liters to the -1. Or if you remember from chapter 1, a liter is also a cubic decimeter. So another way to write this is a mole per cubic decimeter, or decimeters to the -3rd. Here's a sample problem for calculating molarity. Calculate the molarity of 10 grams of potassium hydrogen carbonate in 100 milliliters of solution. So the first step is to write down the equation of what we're interested in, which is molarity, and know that we need to know the moles of the solute divided by the liters of the solution. So the liters of the solution are easy because they're giving us the amount of volume of the solution in the problem. We just need to convert it from milliliters to liters. The quick, easy way to convert from milliliters to liters is simply take the decimal point and move it 3 places to the left. 3 to the left. 1, 2, 3 goes from milliliters to liters. 1, 2, 3. So we have 0.1 liters, which we'd fill in on the bottom right here. The trickier part, though, is getting the amount of solute that they have into moles. And so our very first step is that we have to convert from from grams to moles. So we'll take our 10 grams, write it down, put a multiply sign, put a line, put moles in a position where it's going to cancel, and then add up K, H, C, and 3 O's on the periodic table, which conveniently adds up to 100 grams. So 1 potassium, 1 hydrogen, 1 carbon, and 3 oxygens adds up to 100. And then we take 10 divided by 100 and we get 0.1. Then we take our 0.1 moles and we divide it by our liters, which we already said is 1, 2, 3 to the left, or 0.1 liters. I did that math right down here because there are 100 milliliters in a liter. So 0.1 divided by 0.1 ends up being a 1 molar solution. So molarity, moles divided by liters, we use it all the time in this class. So here's a second question, and this time we're going to solve for something else in the triangle. It says calculate the liters of this 0.5 molar NaCl solution if 58 grams of NaCl are dissolved in this particular solution. So be a critical reader of this and find out the species that we know and the things that we don't know in the triangle. We know the molarity. We know the mass, and from the mass we could find the moles. And if we know the moles and the molarity, we could find the liters, or we could find the volume. So here's the molarity triangle right here. We know our goal is to find this volume. And to be able to find this volume, we're going to have to do moles divided by molarity. But first, we're going to find the number of moles. So we have to take our grams, 58.5 grams, put 1 1 mole, and then add up Na and Cl on the periodic table. Sodium, of course, is 23 right here, and chlorine is 35.5. Add those two together and you get 58.5. 58.5 times 1 divided by 58.5 is 1 mole of NaCl. Now we're going to take our moles and we will divide them by the molarity, cover up the L because we want to know the liters or the volume. So volume is equal to moles divided by molarity. Put in 1 mole on the top. The molarity is 0.5 molar. That comes from the question. So 1 mole divided by 0.5. 1 mole over 0.5 mole per liter, because these are another way of writing the units of molarity. And from here you can see the canceling and how the moles will cancel with the moles. And we're technically left with units of 1 over liters, which you learned in math class. When you have a complex fraction like this, multiply by the reciprocal. So if you take this 1 over liters and flip it over, you end up with liters as your units. So 1 divided by 0.5 turns out to be 2, and so 2 liters is your answer. All right, let's do a different take on it. This time, this sample problem says calculate the Na plus concentration if 53 grams of Na2CO3 is dissolved in 2 liters. So these brackets, when they have a species written right here or a formula written and they put it in brackets, it always means the molarity of, or the concentration of. So if you see something with brackets around it, always know that that means the molarity. So we want to know the molarity of just the Na plus in the Na2CO3. So first of all, write down our equation. Molarity is equal to moles divided by liters. We know the liters right here. We're going to have to find the moles. We're given 53 grams, so we need to find the moles. So using our periodic table, we need to add up 2 Na's, a C, and 3 O's. I do that for you here. So 53 grams in 1 mole, there's 106 grams of Na2CO3. 53 divided by 106 turns out to be 0.5 moles of Na2CO3. Then take that 0.5 moles and we're going to divide it by our liters. So moles divided by liters. So we're told we have 2 liters to find the molarity. And now we have the concentration of Na2CO3. 0.5 divided by 2 is 0.25 molar Na2CO3. I think there should be one more significant digit here because we're given 3 sig figs here and 3 sig figs here. So this is the concentration of Na2CO3, but the question asks what is the concentration of just the sodium ion. And if you remember back from earlier in the chapter, all sodium salts are soluble. And so this ionic species will break up into 2 Na pluses and 1 CO3 minus 2. So our Na2CO3 breaks up into 2 of these and 1 of these. There's 2 Na's inside of here. So I need to take my molarity and multiply it by 2. So 0.25 times 2 ends up being 0.5 molar in sodium ion. So when you're asked to find the concentration of an ion, always remember that you've got to look at the subscripts to find out how many are in a particular formula. So one characteristic of solutions that makes them handy to use is you can dilute them. And by dilution we mean, let's say we have a solution of 100 milliliters of 0.1 molar KBr inside of a beaker. And then to this we want to dilute it by adding 400 milliliters of water. So we're diluting it by adding water to it, H2O. So now my original amount was right here, but I added 400 milliliters of water and then I mixed it up. Remember, a solution is always a homogeneous mixture, which means it's the same throughout, so the water goes everywhere. And it simply spreads out the KBr, or the K plus and the Br minus ions. So the trick to knowing how to do calculations with dilutions is realizing that the moles, or the number of particles of KBr before I added the water, is still equal to the number of moles of KBr after I added the water. Just because I added the water didn't change the number of moles of KBr in there. It changed the molarity, but it didn't change the moles that were in that solution. So using my molarity triangle, I can do some fancy math. Moles are equal to molarity times liters, and so I can substitute molarity times volume for moles here and for moles here. And so I can design this equation that says the molarity initially times the volume initially is equal to the molarity at the end times the volume at the end. I use 1s and 2s just to illustrate the before and after situations. So now I can plug in the numbers that I'm given. If this were a problem, it could say what is the concentration of this KBr solution after I added 400 milliliters. So the original molarity was 0.1 molar, and there were 100 milliliters of solution to start with. And the final molarity is something that I want to know, so I'll write down M2. And the final volume is 100 plus 400, or 500 milliliters. Note that you have to use the total volume at the end. V2 is always the total volume. Solving this for M2, dividing by 500 on both sides, ends up being a molarity of 0.02 molarity. So in this video cast about concentration of solutions, you learned about molarity, and molarity is equal to moles divided by liters, and you can use a triangle to help solve for any one just by covering it up with your finger. Just remember, molarity is equal to moles divided by liters, and you can never go wrong. You learned how to solve this. You learned how to look for concentrations of ions. And remember, if you're asked for an ion like nitrate in aluminum nitrate, then you have to look towards the subscript right here, indicating there's 3 times as much nitrate as there is of the regular aluminum nitrate in the solution. And lastly, you learned about dilution, and that molarity initial times volume initial is equal to molarity final times volume final, because the moles before are equal to the moles afterwards of a solution.